exactly in the context of the neural data analysis. So there is a book that I'm following, which is this one, which actually on which there is a link to the PDF in the Slack channel by very prominent statisticians and data analysts. And so the book follows what is nowadays the dominant paradigm for definitely neural analysis, but I would say all kinds of data analysis, which is the Bayesian framework. And actually today, so I will go through, since it's been a while, I'll give a refresher on chapter 4, which happens to be where the Bayesian framework is introduced. And I'm going to talk a little bit about some examples about how this framework is used. So, and so this chapter has this sort of very obscure name, random vectors, and that needs some unpacking. What they mean here is that we talked about random variables. That is a variable that actually can be probed at different times, so that can come in multiple realizations at different times, and those realizations have some degree of randomness. So, for example, if I throw a die, get a 1 through 6, that is a random variable. If I look at the height of the next person that will pass in the hallway, that will be a random variable. If I get the chance that you get a cold in the next 10 days, that's a random variable. These days it's probably as a probability of 1, so it's not so random, but it's okay. And we talked about how random variables are described mathematically, so with the concept of probability, so that the fact that you associate a number between 0 and 1 to the likelihood that a certain outcome for that variable will occur. And so, and we talked a little bit, and we'll return on that, on what the interpretation of this probability number is. And so we made the distinction between the formal mathematical properties of probability that are quite fixed and beyond discussion, and the interpretation of these numbers, actually on which there is debate. So that is, so now, what happens if you consider situations in which an outcome is not just one number? So for example, now I could say, I'm going to record the weight and height of the next person that passes through the hallway, right? Now you have two numbers. And so these two numbers are interesting because they are somehow coupled, right? So you would assume that taller people are also heavier. That implies an association between these two variables. And the thing generalizes to outcomes where you see many variables together. For example, if you're doing spike sorting, you just have a channel. Each spike will look something like that, right? You have a bunch of points because you are recording this spike with a digital system. So You actually make a measurement of the voltage every, in our case, every 30,000th of a second. And for a spike, typically we acquire, let's say, 24 data points. And each waveform will look a little different. Another waveform looks like that. If you did spike sorting, you are used to this kind of plots. And that means that each waveform is a different realization of those 32 random variables. So the first sample, the second sample, third sample, etc. And we typically write down these 32 variables as a vector, so as a list, and that's its random vectors. That's what that name signifies. And now the key point of, well, if these things were completely autonomous from one another, then you could just treat them everything singularly, and there wouldn't be much to say about random vectors. Okay, yeah, it's a collection of vectors, of variables, but then I treat each one by itself, and I'm done. So the idea is that there is association. For example, there might be a bigger waveform here. And then, of course, so if this data point is more negative, chances are the next one will be negative as well, because it's difficult that the waveform makes a sudden jump and goes, for example, here. Right? Yeah.
So each S is the point, or
each S would be like the first S1. So each one of these is a random variable. And this will be the first sample,
S1.
second sample,
okay.
third sample, fourth sample.
Okay. I thought there were different curves.
No.
Okay.
No. This is a random variable, so this is an abstract object that you can imagine is spewing out different realizations. And sometimes you see a realization indicated with a hat, right? And so there is a difference between this guy, which is essentially an abstract object, so it's a factory of realization, and a realization which is a set of numbers. These are not the numbers. These are random variables. And that means it's a... so they are, in general, these guys can be associated. Now, measures of association is most of what we do in science, right? So when you do an experiment, so you want to know if you vary some variable, so you vary the object configuration, duration of learning, training, puts a drug in the system, and so on. So you want to see what happens to another variable, which is some experimental reality. That's what all you do, right? So that means that actually characterizing these associations is a very important thing. And yes, so this is the example with spike sorting. And so here, so we said last time that we always start from probability distributions. Now probability distributions are, and when you talk about the probability distribution, you talk about, you have a probability distribution for one variable. You can have something that looks like that. That's a Gaussian distribution. And that means that this variable x as a variable, as a value that is the most common, which we call the mu parameter of this distribution. But it's not going to be exactly mu each time, it's going to vary, and how much it will typically vary is given by the width of this distribution, which is indicated by something called sigma. And typically instead of sigma, we talk about sigma squared, and then you have mu and sigma squared that are two parameters of this distribution, right? So that is okay, it's normal. How do we characterize multiple variables? Well, let's start from the case of two variables. So suppose I'm just reading out two things. Again, can be height and weight of the next person coming in the hallway. Now, instead of having points on the line, I'm going to have something defined on the plane, where this is S1 and this is S2, and at each point on the plane, each configuration of the value of S1 and value of S2, I have to associate a probability. And then here, so one way to plot it is, for example, with contour, in a contour plot, I might have something like this, where these are the most likely variable, and these are the second most likely variable, and these are still less likely variable, and so on and so forth. Okay. So that is, and then we talk about the probability distribution of these two variables together, or the joint probability. Distribution. Now, the joint distribution is the most general object. So that is what contains all of the information about the statistical structure of this random vector. So S1 and S2 together. Yeah.
Just to understand the contour plots
Yeah.
a bit better, so we should imagine there is a third dimension, right?
Yeah, that's the third dimension. That would be probability coming out of this.
Right. So the middle circle is like 0.9,
Yeah.
the outer
Something
circle is
like-
0.6, the other one.
Yeah.
So if you choose like 1 point on that graph, so that point means,
Something like that.
so like the top right point means that to observe values of S1 and S2,
Yeah.
those values of F1 and S2, probability is 0.3. or
Something like that. Yeah. So, any more questions? So, I said this is everything, right? I know this, I know everything. However, this is an object that is extremely difficult to characterize in general, and is sort of the more difficult to describe. Why? Well, now, these are idealized case, right? Typically what I have to do, so if I'm trying to say that this variable here is the exploration index of one of your mice, and this is the idealized case, what you do typically is you do many trials with many animals, and you build what's called an empirical histogram. You make, typically you have a binning, it means you divide the possible variables in small intervals, and for each interval you count how many times you see that value. And you get something that is going to be fairly irregular. Each time you repeat the experiment with 10 new mice, you're going to get a slightly different histogram. If you're likely, they more or less look the same, but still different. So what's the problem? So here you have, suppose that here I made a binning in which I divided this range of possible value for variable, let's call it S1, in 10 different bins, or in B different bins. In order to have a histogram that is meaningful, I need to have a few data points in each bin, right? So if I have 20 bins and I have 3 data points, the histogram is meaningless because I just have something here, something here, something here, but it's totally not representative of what's going on. So I need a number of data points that is of the order, I insist on these things because these are very, of the order of the number of bits. Now think of this situation. This situation, you need, now I can still do a binning, but now the binning is going to look like a grid. Look like a grid, and that means that effectively, if I use B intervals to describe the range of variation of one of my variables, S1, S2, now I have B squared bits. And if I have n variables, or n dimensions in my vector, it B to the n. So that might actually add up very quickly to quite a lot. So to go back to the spike sorting example. So if I have let's say 32 data points for each waveform, if I wanted to fully describe all the space, the total joint distributions of these waveforms sampled at 30 kilosamples per second, and I quantize the possible voltage levels in 10 different values. Now I need 10 to the 32 spikes to characterize the joint distribution. That's not going to happen.
Doesn't variability play some kind of a role here? So if all the spikes are usually similar, or no, this is for one single spike, right?
This is for one.
Okay.
This is sort of the ground level, naive representation of the full joint probability distributions for the data point in this voltage space.
And that is like the top grid, that's like 3-dimensional histogram.
That would be, at this point, would be a 32-dimensional histogram. Because you would have, in principle, you would have to consider all the possible combination of voltage levels at all the 32 data points.
If you have 32 data.
Which, of course, also includes, so of course this is super naive, right? Why is it super naive? Because this includes waveforms that completely don't make sense. I could have a waveforms doing this, right? So we know that that's not what's going on. So, okay. So typically what you do is you try to come up with a simpler description. So one way to come up with a simple description is to parameterize your probability distribution. What do we mean parameterize? Well, in essence, I told you already. So suppose that you have a histogram like that. I could say, well, I'm going to assume, and I'm going to be wrong, but not so wrong, that this data I can model with the Gaussian distribution. And then all of this mess of a histogram, I can just summarize giving you two numbers, mu and sigma. So now I'm going from having to give you a number of data points of the order of B to just having to characterize two numbers. Lots easier. How do I do it in this case? Well, there are models there. Next time we'll talk about like the classic probability distributions that are used in addition to Gaussian distribution, like Poisson, Bernoulli, and all this exponential distribution, gamma, and all these goodies that we have. But let's stick to Gaussian distribution for this time. You can have a multivariate Gaussian distribution, where now instead of having a one-dimensional bell-shaped curve, we might have a two-dimensional bell-shaped curve, three-dimensional bell-shaped curve, which you cannot draw by analogy. And that gives you a representation that has a lot less numbers. For example, in the case of a two-dimensional Gaussian distribution, a bivariate normal distribution, as a statistician would say, you have a center point which has coordinates mu1, mu2. There is a variance on the S1 axis, and there is a variance on the Y1, on the S2 axis, or X and Y if you prefer. So it tells you how widespread this distribution is in the two dimension. So we can say sigma 1 squared, sigma 2 squared. And I'm almost done. I need an extra thing, because this bell-shaped curve might be of different shapes. For example, it could look symmetric or circular. It could look very elongated, or could look something in between. So this other way things can vary is summarized by an extra parameter that is called rho, and it's called the correlation coefficient. Correlation coefficient goes between 0 and 1, where 0 corresponds to the perfectly symmetric case, and 1 corresponds to a case where the bell becomes so thin that essentially collapses on a single line. So, what does it mean? Why is it called correlation coefficient? Well, we have to introduce another concept, which is that of statistical dependence or independence.
We talked about it last time.
Yeah. Yeah, but I think it's actually, is it useful that I go through this again?
Yeah, I would also say, I think repetition is really good.
Yeah, because it was more than a month ago, and if we don't agree on this, we won't agree on anything else.
It was last year.
Huh?
It was
Last
last
year.
Last year. It's yeah, almost 2 months. Yeah, so I think we have to do a recap, or we can.
But then again, this was a great memory test. He remembered that we already done it.
So,
Probably not the only one.
so I'm going a little faster than last time. So, what do we mean by statistical dependence or independence? Well, in this case, if you know the value of S1, you know quite a lot about the value of S2. Because if S1 is here, then S2 should be somewhere here. It will be very unlikely that it's here. Vice versa, if S1 is here, then S2 is likely to be here and not here. How do we formalize this concept? We do that with the concept of marginal distribution. That's another kind of beast that P of X and Y, let's just say S1, S2. Okay, this doesn't work anymore. The other one doesn't work either.
Did I get one from the office?
Yeah, they work for a little bit. And then they don't.
Yeah, I think we have more in this.
So then there are these other objects that are just functions of one of the two variables, of S1 and S2. And so this guy, for example, it tells you, okay, I just want to concentrate on S1. Let's pretend S2 doesn't exist. Okay? And so I basically say, I take the overall distribution, the overall probability distribution for S1. So how do you compute that? Well, this would look something like this. Okay. I think this would be that.
We hope there are like 5 or 6 more of these boxes full.
Yeah.
Thanks.
So this is the marginal distribution. So it's the probability distribution of S1, where I say forget about S2. How do I compute it from the joint probability distribution? You integrate, or you could imagine, if you imagine that this was a bell-shaped two-dimensional curve, so assume that that thing was made out of semi-opaque glass. Then I could say, take this curve, just flip it and just look at it this way. Then you would say it's the contour, and that would give you that shape. And if you look at it this way, you get the marginal distribution. Okay, drew it really badly, but on the okay. So those are called the marginal distribution. Okay.
So distribution of one independent of the other.
Yeah. So, and mathematically, the marginal distribution you calculate by integrating the joint distribution over the other value. Now, integrating is a scary word. What essentially it means that I will sum over all the possible values of S2 for each value of S1. So it's an operation of integration or of summing. Now there is a third very important concept, which is the concept of conditional probability. And so that goes back to what I was telling you before, that in a case in which I get an elongated cigar-shaped cloud here, there is an association between the variables. And an association means that if S1 is here, S2 is likely to be in this range, and if S1 is here, S2 is likely to be in this range. So that means that if I know the value of S1, now my expectation about what S2, where S2 is going to be, is changing. Or I can say there are two different probability distributions for S2. One when I know that S1 is here, and one when I know that S1 is here. And one probability distribution will look like this, and the other one will look like this. So same thing, but shifted. And so that would be the probability of distribution of S2, and then I use a bar, and that is red. This is the probability of S2 given S1.
So that's a P, not a row anymore.
It's a P. It's always a P, because these are probability. So these are the different kind of probability distributions we're going to encounter. So you have joint, you have